To start with, I have a question. Does anybody feel strongly about this talk being in English? Is everyone okay with it? Okay. Cool. English, it's gonna be. So, my name's Alfonso Acosta. I'm a software engineer at Weave.works. And today I'm gonna talk about microservices, scalability, and how we applied that to ourselves. I'm gonna start with the classic survey in order to know a little bit about how to address you. So how many in the room have used Docker? Please raise your hands. Okay, in production? Okay, that's impressive. How many of you have used Kubernetes, Swarm, or Friends for orchestration? Okay. Yeah, that counts. Mises counts as well. How many of you are Golang coders? Okay. Cool. And finally, how many of you knew about Weave before today? One hand, that's good. So I'm gonna be doing some preaching now. Actually, it's gonna be a fairly technical talk. First, I'm gonna introduce what's Weave, Weave.works, and what we do. So, as I said, I'm a software engineer there. I've been tumbling around Europe before coming here. It's actually my first meetup in Spain. So I would like to thank Jopental and LiveRay for inviting me. And I'm sure that at some point my English will bit rot, and I'll be doing this in Spanish. So, as I said, I'm part of Weave.works, and what we do is products to help develop, deploy, and maintain internet services. We're particularly targeted at microservice-based applications. I'm not going to talk about microservices because we've talked about it before. And we're well known for a product called WeaveNet. It was the first virtual networking or overlay networking for multi-host Docker communication. Now Docker have their own multi-host solution, but we were the first ones to provide it. But I'm not going to be talking about WeaveNet today. My talk is going to be fundamentally different from the talk you've heard before, namely because we have the privilege of not needing to deal with legacy. We're starting from scratch, which is a really good privilege. And I'm going to talk about how we built our service called Weave Cloud. So I've already talked a little bit about Weave.works, what we do. One of our products is called Scope. We're going to be talking a great deal about Scope. In the previous presentation, you were seeing a lot of diagrams about how things work, right? And as engineers, we typically find ourselves drawing arrows and boxes on boards. And more often than not, we don't get things right. We draw them, and then we need to think about it. And then after the chat we've had with the colleague, we go back to the source code, and okay, that wasn't really how it worked. So what we built is a service which helps you visualize, monitor, and see exactly what's happening in real time with your microservice-based applications. That's Scope. And we built a service around it, which we're going to extend with other things like integrations with WeaveNet, integrations with Prometheus, if you know what that is. I'm sure you guys do. So today I'm gonna talk about how we built that, how we got it horribly wrong at the beginning, what happened after we rebuilt it, and some nuances we found on the way. It's still not perfect. It doesn't need to be perfect. It's good enough for now. And by the way, I'm very generous, and I like these things being interactive, and I like sharing the anxiety of being here. So I want this to be interactive. Please stop me if you have any questions. I don't mind if we get to the third slide as long as we make it interactive. I don't want this to be boring. Normally, I don't make enough slides for the half an hour because I want it to be interactive. So please, do interrupt me, ask questions, and I will ask you questions too. So I'll make sure it's interactive. So let's start with a little demo here. What you see in that screenshot is a screenshot of scope. And I'm going to show you exactly that live. So we built a microservices reference application because we often encounter ourselves trying to think like clients, how people build microservice applications, and there wasn't a whole lot of that out there. A lot of big companies like Netflix, Spotify, and Friends were using microservice-oriented applications, but their code wasn't public, or in some cases it was too complicated to recreate. So we built our own reference application, and it's a sock shop. It's not really relevant, but it's good enough to show you how Weave scope works. So what we see here, actually, it's a sock shop. We have a high contrast mode for presentations like this one. Let's see. Can you see it? Is it clear enough?
Yeah.
Okay. So this is a canned demo. It's not a living system, but we have it for demo purposes. But it's good enough to get a grasp of what scope does. It makes you it gives you a graph-like representation of your microservices and how they talk to each other in real time. You can inspect these. What you're seeing is a container view. You're seeing that there are internet connections going to an edge router, to the front end, to something called logging one. You can see to what networks, what Docker networks each container belongs. You can see details on each of the containers. You can see the same view through processes, which is a bit too detailed in this case. You can see the hosts, how they talk to each other. In this case, we're seeing a deployment based on Docker Swarm. It's all good and dandy, but this is not real time. So I want to show you the representation of the service itself monitored by scope. It's going to get a little bit meta, but bear with me. So what you see here is the actual Weave Cloud service monitored by scope itself. Let me get the high contrast mode. In this case, it's using Kubernetes. We're going to talk a little bit about that. And you're seeing the services view. You can go to the deployments view. You can go to the containers view. You can see details on them. And not only can you see what's happening, but you can also interact with it. Let's see. Let me get a container. Yeah, we have the auth front end. We can open a terminal there and see what's happening. We can get the logs, so on and so forth. Okay, I didn't mean to do this as a marketing move. I want you to understand how the application works before we dive into the architecture. Any questions so far? No questions. I don't believe that. Okay, there you go. Should we use a mic?
Oh, yeah, sorry.
Okay. Oh, by the way, all of this, most of it actually, it's open source. It's on GitHub. There are parts wrapping the service, which are closed source, like authentication and so on, but the core components of scope are available on GitHub, and they're implemented in Golang.
So you have showed us it works with Docker Swarm and also Kubernetes. Mm-hmm. And does it work with any other orchestration? Like
it works with Mesos. It works with ECS. In fact, Amazon themselves show scope in their talks. It works really well with ECS actually.
Okay. And second question: how does this service discover the routes between the containers? in Kubernetes?
Well,
it's an agent that you install on each.
Yeah, we're going to talk a little bit about that. I mean, I could talk, there's material for another talk on how we gather information about connections and how we do it the way we do it and not the way Sysdig does it, for instance. They use the kernel module for it. But yeah, actually, I'm giving a talk next week in the Docker meetup, and I'm going to be talking exactly about that. But we can chat about it after the talk. Any other questions? Okay. So let me explain a little bit how Scope standalone, so the pure open source version, works. You run something we call a probe in each of your hosts, which gathers certain information. Similarly, that information we call reports, which work similarly to CRDTs. Does anybody know what a CRDT is? Okay, it's called conflict-free replicated data type. It's a distributed data type which you can update without consensus with the rest of the hosts which have that information. Basically, it's a data type with merging semantics which don't require consensus with anybody else. You can resolve conflicts yourself. So we gather those reports. We send them to something we call Scope Up. We merge them together, and we send them to the UI. And in the other direction, as you saw in the terminal and so on, we have something called controls, which allow the UI to interact and perform actions on the resources managed by the probes, like a container, the host itself, and whatnot. So the CEO of the company came to us and he said, oh, we should build a service around this, of course. And we did that. And I was in London at the time, and everything important was decided at the pub. We went to the pub, we sat down for a couple of hours with a few pints, and we came up with an idea. The super minimal viable product was, it needs to be multi-user, it needs to be authenticated, and we need it now. So this is what we came up with. It was invite-based. You didn't need an automatic invite system. Whenever somebody requested access, the product owner would look at them, send them an email, and click on OK. We built a small wrapping around the open source scope. So we built an authentication layer. We called it user service, and we also created a multiplexing lazy deployment service, which we call that mapper. We used AWS for it, and we decided to use Docker Swarm because we were familiar with the Docker API. And for those not familiar with it, the Docker Swarm orchestrator exposes a very, very similar API. It's actually a superset of the Docker API. And we use Terraform for creating the infrastructure and actually managing containers, which was a terrible idea because it worked like crap. Don't use Terraform to manage containers. And this is what we came up with. So we said, okay, we had our beautiful scope with probes talking to an app, talking to a UI. So let's try to extend it in the simplest way possible. So here we have our users, who have a few probes running in their hosts, and they connect to the Weave Cloud service. They all connect through the app mapper, which has a database and knows whether that user has a mapped app. If it doesn't, then it deploys it. That's what I meant by deploying it lazily. And each user has a single app to talk to. And then we have the user service. So for every request, the app mapper with some caching, or maybe we didn't even have caching at the time, I don't know. It talked to users, and he said, and we authenticated the cookie or whatever scheme we were using at the time. And we did this in November 2015, and this was up for 6 months, I believe. But there's a few things which are wrong here, but I want you to help me out with it. So what's wrong here? Don't make point at people. People hate that. Come on, guys. So what's wrong with this?
Bottleneck.
There's a bottleneck in the app mapper. Well, we don't have that many users, so.
Single point of failure.
Right. The apps are a single point of failure. So if one app goes down, then that user cannot use the service. That's one. Anything else?
The users is not really microservice because you are really
Yeah, that may be true, but that also wasn't a problem. With the caching layer, that was fine. Anything else? By the way, for the mic, they were saying single point of failure, scalability, because of the app mapper, everything was routed through the app mapper. But actually, you could have many of them, right? And we did, because everything was hitting the same database. So in terms of the service itself, you could have it replicated. And they've also mentioned that users wasn't really a microservice. I actually don't totally agree with that, but fine. Anything else? Okay. So Swarm was painful to use. The Docker API was nice, but insufficient. There's a lot of abstractions you want to use when deploying a service, which cannot be extrapolated from managing a single container in a machine, which is what the Docker API was built for. And it was buggy as well. We found quite a few problems there. It didn't have things, maybe it does now, correct me if I'm wrong, but at the time it didn't even have blue-green deployments. You couldn't basically update the service without having downtime, which we didn't want to have. And then, as it was pointed out, we had a per user scope up, which if you're familiar with Adrian Cockrop's pets and cattle metaphor, who's familiar with that? Okay, can you explain what that is?
Well, it says that when you have on-premises machines, virtual physical services, they are like pets.
Okay.
If your pet dies, you are very sad.
Right.
And with virtualization and cloud, virtual machines or containers are like cattle.
Right.
If one of your cows die, you have another 100 of them.
Which is, if you apply it to specific instances of your service, that's exactly what happened here. If one of these guys went down, we were going to get really sad. Well, the user was going to get sad, and in turn, we were going to get sad. Single point of failure, and actually, a really important point is we have resources wasted. If this guy connected for 5 minutes, and then he never connected again, his instance is going to be running. Maybe not consuming a lot of CPU, but we ended up needing to do some sort of garbage collection for instances. And when you had to upgrade the system, imagine changing the cluster, and you have stateful information of what's running here. You need to make sure you clear out the database in a specific way. You don't want to deal with that. So how would you solve this? Any ideas? I'm not going to point at you, but I want ideas. No ideas? Okay. So for the Swarm part, we moved to Kubernetes, which has a lot of nice things and a few not so nice things. And for the pets versus cattle stuff, we moved to a horizontally scalable service in which you could send, a user could send a request to any of the instances running. We implemented specialized instances, so it wasn't just a single type of app. It was specialized based on the task it was going to perform. We're going to talk about that. But first, let's talk about Kubernetes. Who has used Kubernetes again? Hands? 2 hands, 3 hands, 4 hands, 5. Okay. It has a very rich set of abstractions. It lets you deploy things in different ways. It lets you do rollouts. It's done the Google way, which is very, very opinionated, inspired by Borg. And yeah, maybe the amount of abstractions, it's a bit too high. It has a very steep learning slope. It took us, and we're not newbies at this, it took us 2 weeks to read about it and fully understand it and start, to get a grasp around it to migrate the service. They're trying to change that by minimizing the core functionality of Kubernetes. We could do 0 downtime deployments because they implement rollouts. It has a very, very strong open community in which we're taking part, actually. But as another drawback, the installation and upgrades are really painful outside the infrastructure, the cloud offering provided by Google, JKE. We actually have a blog post explaining what was our experience there, if you want to have a look at it. And we're actually helping out with installation and upgrades, starting with Kubernetes 1.4, which I believe is going to be released next week. Weave.works has been in charge of implementing a tool called kubeadmin, which simplifies installations. So the other problem was making the app scale horizontally. So what we did instead is, the idea was, let's have a bag of apps which we can scale in number in the way we want, and any user can connect to any app. And what we did is we specialized the apps based on the functionality, and that's exactly why I wanted to demo the app, so that you understood the breakdown we did. So we implemented a collection service, which is in charge of collecting the reports and storing them. We implemented a query service, which was in charge of gathering, retrieving those reports, and sending them to the user. No matter what user was connecting, the query service would connect to a common storage layer and gather the specific reports. We broke the app in 2 other services, control, which applies actions on probe resources, create a terminal, show logs, so on and so forth, and something called pipe. So the control does an action, and the pipe then takes over and takes care of the bidirectional communication between the UI and the app and the probe. Any questions? Maybe this is a little bit unclear. Is it clear? Judging by the faces, it's not clear. Okay, so let's see it live. Yeah. Can you read the tags on the nodes? Is it readable? Okay, let me zoom in. I don't want to apply the zoom in feature of Chrome because the front-end engineers are going to kill me if I do that. Can you read it now? Okay, so this is structured in the direction in which we the communication flows. So external connections are going to something called auth.fe, authorizing front end, which actually communicates to a user service and has a caching layer. And then auth.fe forwards the connections to a collection service, a control service, a query service, and we have some other services in terms of storage. We have NATs, we have Memcache, and then we have a separate UI server which serves static content like the JavaScript, so on and so forth. We also have console, we have the pipe service, which right now is not being connected to. But let's talk about that in a little bit more detail. So what we did was break down the service and break down the app in 4 different services. collection, storage, query, retrieval, control, actions, pipe, bidirectional communication. And each of those use a custom storage. For collection, we use Dynamo, S3, Memcached, and NATS. But let's concentrate on Dynamo first. The original idea was to use scalable, eventually consistent storage. We could have used Cassandra, for instance, but we decided to use Dynamo because it's very simple to use. You don't need to worry about maintaining it, so on and so forth. It was a conscious decision. But when we deployed it for the first time, we noticed that the size of the reports were killing us in terms of pricing. So what we did is we broke the storage level in two parts. We used Dynamo for indexing, so know when our report arrived and from what user. And then an S3 layer, which stores the objects. Actually, we don't really need the S3 layer. We could have used a queue because it's ephemeral. We're showing things in real time, but at some point we want to implement a historical. In front of S3, we had a memcache. We placed a memcache layer because it's expensive to talk to S3. Actually, the heat ratio of the cache is pretty high. And then we included NATS to implement support for something called shortcut reports. Imagine that you're viewing your containers and all of a sudden one container dies or stops or something like that. You don't want to wait until the next query. So a shortcut report is sent directly to the app and the container disappears. Then control pipe. For pipe and actually for query as well, latency is important. You don't want the user to wait a lot of time when they click on the UI. And you don't want users to wait a long time when they type on a terminal. So for pipe, what we did is we implemented we used console, which is a strongly consistent storage. I believe they internally use Raft, doesn't matter, to implement the rendezvous between the app on the probe and the probe on the UI on the app and the app on the probe. And something similar we implement with SQS for controls. In this case, latency is not super important, so we can use a queue directly. Because if you press stop on a container, it's not critical whether it takes 1 second, but it is critical if you type a letter and it doesn't appear in the terminal until 1 second passes, right? And yeah, you could argue, okay, this is a lock-in. We've been told several times you should be wary about using external services from a cloud provider, but we did it consciously. Maintaining, from our experience, maintaining Cassandra, maintaining storage layers for a team this small, we're around 10 engineers, I believe. It's not worth it. We'd rather move fast. And they're easily replaceable if we need to do that at some point. But we did all this, but we were still sad. Very, 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 very sad. Because the query service had a latency and 99 percentile of more than 4 seconds, which is terrible. Imagine clicking. That's really bad, isn't it? And we digged into it for a while. I could have a whole presentation on this. But the reasons for that were basically, we're using big and optimized reports. The information we provide is highly redundant. We want to keep using the CRDT semantics, and we want to use the immutability around it. So you send a report, and 3 seconds after that, you send another report, and you send another report with the same information. That's not optimal from the performance point of view, but in terms of reasoning around it, it's really easy. You don't need to worry about reports getting lost. You don't need to worry about cross-references between reports. A report is self-contained, and it provides self-contained information. But they're huge, 10 megabytes uncompressed, and at a frequency of 1 report every 3 seconds. So for clients with huge clusters, that's a problem. And you could argue we were carrying out a bad use of immutable persistent data structures. Who can tell me what a persistent data structure is? Okay, a persistent data structure is it's an immutable data structure. It's a data structure for which older versions are never modified. So imagine you implement a map, you include a new key, but the previous data structure is not modified, and you can pass it around threads without worrying about it. That's all beautiful and dandy, but it comes with a performance impact. It's really good for reasoning, right? Because you modify your map, you share it with threads, which is how we implement reports in memory once you deserialize them. But it's not really good in terms of performance, particularly in Go. So what did we do? We improved report decoding. We used a custom decoder, generated a compile time, which is not really the final solution for the problem, but it helps us get going. We improved the use of the immutable persistent data structures. There were a lot of, let's copy this data structure, just in case, because maybe someone will modify it somewhere. So let's return a copy of it without thinking too much about it. But each of those copies generated garbage. And as we'll see, Go is not good at throughput in terms of garbage. We also improved the external map library because, persistent data structures in Go. Let's see what's in GitHub. Let's use this. We were happily using it, but well, we'll see an example at the end in which it wasn't all that great. And believe it or not, choosing the right EC2 instances helped so much. The service was such a CPU bottleneck that reducing the amount of instances, but making them much beefier helped a great deal. And we were paying exactly the same amount of money for it. So it's a small detail, but with a big difference. So with all those mitigations, we went down from 4 seconds to under 200 milliseconds, which is more than acceptable. But it won't cut it in the long run, because what we're doing by using beefier EC2 instances is scaling the service vertically. And you have so many cores you can add, right? Optimizing the report format, we should do that, but we're reluctant to do that because it makes reasoning about the service very, very difficult. If you have delta reports which are referencing each other and one of them gets lost, what do you do in that case? How do you deal with that? Then you have a stateful storage, whereas right now we have a beautiful full report storage in S3 in which you look at each of the reports and you have your final information. Get rid of persistent data structures. Sure, we could do that. Again, it would make reasoning about data structures more difficult. Or maybe we could have a report merging service. Yeah, it could help in cases in which you have a lot of reports to merge and you can break the merging into different machines, but the bottom line problem is still going to be there. How are we doing in terms of time?
5 minutes more.
Okay, we can cut it here.
It's actually out of time.
Okay. Yeah, okay. So I had a few slides about persistent data structures and how we dealt with them. I'm comparing garbage collectors in Haskell and Golang, which I find very interesting, but maybe it's really boring. So
I think that you can go for 5 more minutes because the business just arrived.
Okay.
So they are going to leave out anyway.
Sure. So as I mentioned, persistent data structures have a property in which operations never mutate previous versions of the data structure, which is great to reason about, and it's great because you don't need locks. But it's not that it's good to have garbage collection to deal with previous versions. You really need garbage collection. I think there's theoretical proof that you cannot deal with them without that. And it generates large, huge amounts of garbage. I was in charge of debugging this, and I was hitting my head against the wall with this for a couple of weeks. And my colleagues were telling me, one in particular, dude, we need to keep this persistent data. It's good to reason about them. Actually, I think we can get a performance gain, which is true in some cases. So I looked at what was happening, why Go performed so badly in that case. And it turns out that Go is not meant to use persistent data structures. The garbage collector is designed for latency, not throughput. Have a look, for instance, at the Haskell garbage collector. It's built precisely for that. It's a pure language, there are no side effects. It needs to deal with garbage and have a high throughput in terms of dealing with garbage. It's generational, compacting, it stopped the world, it doesn't need to deal with blocks while it's garbage collecting, and it exploits properties of pure data structures. It knows that a data structure you're creating now can never reference all data structures because mutability doesn't exist out of the I/O monad. And they get away with it. The throughput's really high. On the other hand, Golang's optimized for latency. It's a concurrent, tricolor garbage collector. It stops the world, but very, very little, and as little as possible. And it's good for services because it won't happen like it happens with Java, in which things stop. And then you need this guy who has the role of tweaking gears to make the garbage collector perform in the way you want. And actually, scape analysis needs serious improvements. Does anybody know what scape analysis is? So scape analysis, when you create a variable in a modern programming language which has a garbage collector, the runtime of the language has a choice of creating, in many cases, in some cases it's explicit, like in some languages, but it has the choice of choosing between allocating the variable in stack or allocating it in heap. Stack is faster. You only need to modify a pointer. You don't need to do any bookkeeping around it. But of course, you need to be careful about that, because once that function returns, the scope of the function goes away, and if by error you've created the object in stack, you're screwed. So Go is not good at that. And I had an example on why it's not good, but let's cut it here and have some pizza. Questions? No questions? People are very hungry. Okay, let's sit then.
Thank you very much.